So, Dr. Jill Ellenbarger is an assistant professor of chemistry here at Dunbar. She received her bachelor's from Union University in chemistry and a Ph.D. in inorganic chemistry from Texas A&M University, where she wrote her dissertation about theoretical and experimental investigations in anion interactions in organic biological supermolecular technology. Kind of much what we talked about tonight is the research that she does here at John Brown, supported by the Scholar Fellowship and Christian Scholars Foundation about her computational research in chemistry, about coming up with methods to design color-changing urea-based receptors that selectively identify the presence of various contaminants in water. In addition to chemistry, Jill loves Jesus, her husband Michael, spontaneous adventures in high school. So, please give a warm welcome to Dr. Jill.
Thank you so much for that introduction. Well, it is a joy to be here with you guys and just to share this Tuesday evening with you and talking about science and all the cool things that are involved with that. So thank you for joining us, for joining me today here. So today I want to tell you a story about how God has showed up through science. And not only the fact that God is the designer of science, but that we have an opportunity to respond to Him in that role. And so I want to share with you a little bit about supramolecular chemistry and stewardship and a lot of exciting science. So here we go. So this story began several years ago. I received an email from a friend of mine who's on the mission field in Kenya. And she was emailing me about water that they'd been drinking out of galvanized water tanks that were stored in their attic. And they'd been drinking this water for several years, and then they found out through a series of problems with health effects that they were drinking water that was contaminated with fluoride. So fluoride is an anion, and in high concentrations, above 4 parts per million, has pretty significant health effects. And the water that they were drinking was at 5.9 parts per million. And so this is a really significant problem. And so she emailed me to ask, you know, I remember you're studying chemistry, right? Can you help me? Okay, can you help me with this question? With the fluoride in our water at such high concentrations, would it have reacted with the galvanized water tanks? And so I had a really unique moment of like kind of separating myself from the moment and being like, wow, like I'm a chemist. I'm supposed to know about chemistry. Wow. And this is a real life chemistry problem that friends of mine are being influenced by on the daily, right? And so, yes, I was studying chemistry and wow, it's a really big life question that she asked me. Unfortunately, my expertise was in the theoretical and experimental investigations of anion-pi interactions and inorganic and biological supramolecular architectures. Wow, okay, so what that means is that we have a question that we want to answer about very weak interactions between anions, so negatively charged particles, and organic compounds, or potentially biological compounds, or if we're getting crazy, inorganic compounds. Okay? So we have this question that we want to answer about these very weak interactions. And so we use experimental work and computational work to then get to this idea, like, oh, okay, we're understanding these weak interactions. So that was what my research was looking at, really, really weak interactions. Unfortunately, even though I had a significant desire to help my friend and to answer her question, in no way did my expertise truly 100% apply to the question that she was asking. So even though I had a really big desire to understand all the chemistry and apply it to her question, the reality was that I couldn't really help her. I directed her to some people that might be able to help, but that was kind of where my answer to her stopped. And this was a pretty harsh reality to me. As a student of chemistry studying anions, her anion question could not be answered by my PhD level expertise. Okay, so that often is a reality. And so today, instead of just you guys sitting there and consuming the science that I'm going to throw at you, I want you to be interactive. So I'm going to have several questions that you're going to get to discuss at tables. I like that you're at tables. So at your table, start by introducing yourself. What's your name? Who are you? And very briefly, have you encountered a problem that has been related to something you're passionate about? Perhaps something you're passionate about and you're studying it in school, but you can't yet solve that problem. Okay, so take a couple of minutes and then we'll keep going.
Who are you guys? I think I've seen you before. So it's something I can't solve quite yet. I'm a mathematician. None of my skills have been used. Actually, it's kind of like good questions, like, can this be done? Like, sure. Not really engineering, but like, I can probably tell you how to tell you how the forces should work out. I can tell you this or that. I teach a course on discrete math, and most of the students in there don't work with science. I can't write the code, I can tell you what I should do, I can design what I should do, I can write the algorithm I should do, but I can't actually program it. So, it's kind of an interesting thing. I have math is you can't help the student, you can't answer the questions, you can try.
I haven't understood anything other. All I can speak is okay. Tashiwa Chizuo Tablet.
Okay, guys, you wrapping up your conversations. I hope this is just spurred ideas, and we'll keep going. Okay, so maybe right now you have a problem in mind that's like, oh, I wish I could solve this problem, but yet I can't. I cannot do it. So for me, that problem was the problem of water purity. So I began to dig into what is the actual situation in the world. Okay, so here I have taken the 7.6 billion people in the world and represented them by 10 stick figures. Okay, so we've got each person represents 10% of the world. Yes. And so if we think about considering our worldwide population, 3 out of every 10 humans on the planet lack access to safe water at home. 3 out of 10 people. That's significant. If we broaden this conversation to how is water managed, 6 out of 10 people experience inadequate management of their sanitation opportunities. These are really huge numbers. I was trying to wrap my brain around 2.1 billion, with a B, billion humans. That's an incredibly huge number. And so this is an incredibly huge problem. Not only do 3 out of 10 people lack access to safe water at home, but if we consider just one of those humans, so 1 out of every 10 people on the planet. Okay, so 10% of the world lack a basic drinking water service. Okay? And so they don't even have the opportunity, like the service of water being nearby. Of those, 3.5% of the entire population of humanity spend about over 30 minutes collecting water outside of their home, traveling to collect water. Okay, also part of this 10% of people, 2% of those people, they access water from untreated surface sources. So streams, ponds, rivers. That is how they access all of their water. Okay? And so this is a challenge globally. This is a really big challenge. But the challenge is not only access to water, but also quality of water. Okay? So in addition to many humans being impaired in their access to safe drinking water, is this idea that water that they may have access to may be very contaminated. Okay? And so there are several classifications of contaminants. One of them being microbial contamination. Okay, microbes in the water. So beyond just like boiling the water, you can add disinfecting agents to eliminate microbial contaminants. And this is an important step to immediately disinfect, immediately to remediate this problem. Secondly, you can have radiological contamination. So radioactive materials can contaminate water. Often for radiological contamination, identifying the source and solving the source of the contamination is the most cost-effective way to resolve this problem. Okay, so then we get to chemical contamination. Now, chemical contamination is a little interesting. When there are really high levels of chemical contaminants, it tends to render water undrinkable. You just can't drink it. Your body will reject the water, yes. But whenever you have lower concentrations, that's where chemical contaminants really begin to be sneaky. Like my friends in Africa. The contamination that they experienced was, relatively speaking, lower level fluoride concentrations. But because they ingested these lower level concentrations over an extended period of time, they had significant and long-term health effects. And so the concentration of these chemical contaminants is very important. Once chemical contaminants have been identified, again, it is most cost-effective and time-effective and resource-effective to go and find the source of the problem and to fix the source. And that way, you just purify that, like the source no longer is contaminating the water, and so you're good to go. So here we see that identifying that there's contamination in the water is absolutely key whenever we're dealing with chemical contaminants. And so this is where supramolecular chemistry comes in. Okay, so many times when people think about chemistry, besides loving it with all of their heart, what they might think about is atoms and trying to understand the atom, and then having those atoms bond through like covalent bonds to form molecules. Like, oh, great chemistry, this is it. Okay, well, this is just the beginning of chemistry. My favorite branch of chemistry begins with molecules preformed. Okay, these are my building blocks. And I take these molecules and then I do really, really cool things with them. Okay? So, those of you in the audience that recognize this structure, you are loving supramolecular chemistry. Because the molecules, the base pairs here, that are important, right, are interacting with each other specifically through interactions. And these interactions are weaker than a formal chemical bond, and they go across molecules. So they are called intermolecular interactions. So if you think about driving your car down the interstate, it crosses through multiple states. Okay? Similarly, intermolecular interactions cross through different molecules. Okay? They go in between. And so these interactions are incredibly important. They are not only incredibly important, they allow us to be so creative in chemistry. Because we have a toolkit of all of the molecules you could ever think of, and then we can do things with them with interactions that are just really variable. Okay, so supramolecular chemistry here allows us to be quite creative. Whenever we think about specific tools of relating these molecules, there are specific types of interactions. One that we're going to talk a lot about today is the ion-dipole interaction. So a charged particle interacting with a polar molecule. Now this polar molecule is shown to you, we've got water, so oxygen bound to 2 hydrogen atoms, and now the chemical bond between the oxygen and the hydrogen atom, right, is where electrons are shared. But oxygen and hydrogen, they don't share electrons evenly. Okay, it's kind of like whenever you were playing on the playground, okay? The bigger kid, the oxygen atom, steals the electrons away more often. The electrons spend more time by the oxygen than they do by the hydrogen. So what that means is that the hydrogen kind of feels lonely, like it doesn't have quite as many electrons as it would like. It feels partially positive. Okay, but the oxygen has kind of stolen those electrons and it feels partially negative. Electrons just spend more time over here. So when we think about anions, they interact with the partially positive end of polar molecules. That is the long description of ion-dipole interactions. Okay, but this is the idea. Whenever you have polar molecules, they can interact with each other. These dipoles can interact with the partially positive side and the partially negative side of the nearby molecule. This is quite important for water molecules. This is why water is liquid at room temperature and why ice floats. All good things. Yes, polar molecules interacting in dipole-dipole interactions. Hydrogen bonding is simply a special case of these dipole-dipole interactions. Okay, then finally, London dispersion forces. These are just interactions between molecules that exist for all molecules because all molecules have electrons that are running around them. This is just kind of where electrons randomly will slosh around and they'll like be more on one side than the other, and interactions between molecules. The main point here is that molecules and atoms and ions that have more electrons have stronger dispersion forces as those electrons run around them. Okay, great. So now we have our tools, ion-dipole interactions, dipole-dipole interactions, and then these London dispersion forces that apply to everything. And so when we think about these, while there are other special cases, okay, one of my whole dissertation is about a special case interaction that's not even on this screen. That's crazy. But anyways, when we think about these, there's a lot of creativity, and we can do a lot of things with these interactions. We can design functional properties of large macro-scale molecules. We can develop systems that self-assemble based on the types of materials that we add to the system. And the self-assembly is driven by these intermolecular interactions that we design. And then finally, we can use these intermolecular interactions to develop host-guest systems. So host-guest systems are where there is a host that envelops a guest. Okay, our guest here is the anion. And we're going to talk more about these host-guest systems for the rest of the day. But before we quite get into all of the pieces that go into this design, I want to stop us right here for one more other thing to think about. Okay, so as I was learning about supramolecular chemistry, and as I was learning about the global reality of the water situation, I began to see how these were converging, how perhaps my chemistry could help work on a problem that was really significant. As I was considering these things, a couple of passages really came to mind. So in John 4, this is the story of the woman at the well, and Jesus is talking to this lady, and he says, "Everyone who drinks of this water will be thirsty again. But whoever drinks of the water that I will give him will never be thirsty again. The water that I will give him will become in him a spring of water welling up to eternal life." And so as I was just thinking about this idea of contaminants in water, it's really important to help provide access to people to safe water, to pure water. Oh, but how much more important is it to also, in addition to that, help provide access to the gospel, right? To Jesus, who then provides the Holy Spirit and this wellspring of life, right? But just like the fact that if people can't tell that their water is contaminated with chemicals, they won't know to go find a solution. The same applies to the gospel. If people don't know that there is good news, they don't know that there's good news. And so just like my opportunity to know supramolecular chemistry provides me the opportunity to steward that information and to push towards a chemical solution, I also am called upon to steward the understanding of the gospel well, as I also share that with people. Okay, and so these paralleled for me based on these sources. And so the question that I asked is that can I design receptors that will identify anionic contaminants in water to help people identify that they have a problem? And likewise, will this help facilitate conversations about people's need for living water? Good questions, good questions. I want you to think about some other questions. What could it look like in your life for you to steward your education in whatever your major is? For you to steward that well, okay? So no matter what your major is in, what could it look like for you to steward that well? So again, let's take another minute and a half, 2 minutes, talk amongst yourselves, and we'll keep going. Okay, well let me tell you a little bit more about this idea of host-guest systems, because this is how I want to share with you how I stewarded supramolecular chemistry, or how I'm beginning to steward supramolecular chemistry, how I put it that way. Okay, so whenever we think about host-guest systems, there are several pieces pieces that we need to take into account. The first is that the host, okay, this compound right here, needs to have an architecture that is appropriate to fit the guest, to be complementary to the guest. So this is going to be related to the size of maybe the cavity where the guest is going to be sitting in, the shape of the cavity, depending on what components are kind of pointing at that cavity, that's going to be important. And then also how floppy are the arms on this molecule, okay? How much can they move around? The architecture is quite important, but also the energetic environment of the host is also quite important. Do the interactions between the host and the guest, here we have ion dipole, they're quite close to hydrogen bonding type interactions, but ion dipole interactions between our host and our guest, are these interactions greater than the interactions that the guest experiences in water? Okay, so here we have our anion interacting with water, right? And water molecules will be around the anion and lots of interactions there. So in order to design a suitable host as an anion identifier or receptor, it has to have the right shape, and it must have interactions strong enough to entice the anion out of the water. Okay, so that those are favorable interactions. Whenever we think about designing hosts, I am really looking at using urea, a simple organic molecule, and this is urea here. Nitrogen bound to carbon, bound to nitrogen, with a double bond from carbon to oxygen. And then each of the nitrogen atoms have at least one hydrogen sticking off of it. That is urea. Okay? Urea is quite an exciting compound in chemical terms. So let me tell you why it's exciting. It is quite pervasive in biology, but I love it because in supramolecular chemistry, I am able to decorate this molecule all day long. Can you see this hydrogen right here? And that one right there? I can put whatever I want on there. That's so exciting, yes. Yes, chemistry excitement, wow. Okay, so I can decorate this urea in a couple of different spots, which means I can change its functionality quite dramatically as it interacts with anions. Okay, now these anions that are contaminants may come from a variety of sources. Agricultural, natural, industrial, all these sources, right? We could have anions coming into the water from any of these sources, but we're going to focus, I really care about fluoride, and I really care about nitrate. Okay, fluoride, I've got a personal vendetta against fluoride concentration, but also nitrate is a really important anion when it comes to agriculture, but too much in our water is quite detrimental to our health. So these are the anions that I want to target long-term using urea and decorated urea compounds. Okay, now I'm stepping into a field of urea-based anion receptors that is quite broad. There's a lot of work that's already been done. These are quite exciting, beautiful structures. Yes, we've got urea. You can have either oxygen or sulfur here. That would be thiourea. And so here we've got a urea with a couple of phenyl group decorations off the edges. Here we've got a urea group, and then this subunit will change color when an anion is introduced to this compound. We've also got even more complex urea-based systems. So here we have a rather beautiful structure with 3 urea groups here at the end. And so the anion would fit right in that beautiful little cavity all to itself. It's quite lovely. And then also we can have some of these bis-urea, just so there are 2 urea groups separated by a bridge, this bis-urea compound. Here we have one that fits nitrate quite nicely. So here you see lots of examples of urea receptors, but the one that I get most excited about is by my guy, his last name is Hay. He's been working using computational software programs to take these ideas and predict lots of different potential bridges and come up with urea-based receptors that are selective for anions. This is really what I want to follow in his footsteps and also go down this direction. He was looking at anions that I'm super interested in. He looked at sulfate in particular. And this is a structure that he developed. And this has nickel at these 4 corners. Technically it's a cube, so 8 quarters. And it self-assembles around the sulfate anions in solution. Quite fun. Okay, but all of that to say, computational software programs can be used to help us filter out all of the ideas we could possibly have. Okay, and that's what my group is doing. Here they are, look at them hard at work. We're looking at the computer because that's where we're doing our work. Right now, I'm purely a computational chemist. I want to understand what are the interactions between these urea compounds and the anions that I'm studying, or that we, as my group, are studying. And so the interaction energy is the key. This is what I care about. What is the interaction between the urea and the anion? So in order to break down what delta E, or the change in energy, means is that the complex bound to the chloride would calculate the energy of this complex right here. And then we also calculate just the energy of the receptor and just the energy of the anion. So the interaction energy of the urea with the chloride is the complex's energy minus the sum of the parts. So complex minus urea plus chloride. Okay, so when this calculation is done, use Excel to do this. We don't do this by hand. Excuse me, let me back up for a second. We use Gaussian to calculate the actual energies of the molecules and the ions. And then from Gaussian, we're able to put all of those numbers in Excel and crunch out interaction energies. Okay? And so what we want to see are large negative numbers. The more negative the number means that this complex is really stabilized by binding the anion. Okay? Whenever we think about just the way that we describe energy, more negative of an energy means more stable of a complex. Okay? Now, this is a long quote from a paper. Basically, what it says is that there's a lot of work that's been done in this urea anion receptor field, but the future is combining synthesis and computational work. And so we are stepping into this future, okay, by just doing exactly that. So I've got 3 people on my research team. Okay, so first up, we've got Caleb. Caleb is looking at the architectural component of exploring our urea receptors. So he's asking a couple of different questions. First of all, he's looking at, if I have 2 urea units, and they are bridged by some thing, okay, some type of bridge, and then they're interacting with an anion. Based on the anion that they are interacting with, what is the best bridge for this anion, okay? And so he just began, and so I'm really excited. He's got several calculations in the works, and so excited to see where this goes. He also was really interested in this complex right here. This is not a urea-based compound, not yet at least. It instead is a hexapeptide that selectively encapsulates chloride ions. And so Caleb brought this to me, and he was thinking that perhaps instead of just this peptide piece, he could insert a urea group in these positions, providing more interactions between the anion and the compound, therefore encourage stronger interactions. Like, great, okay, awesome. So this is another question that we're asking. And so the idea here is developing the architecture. How do we understand the architecture? Okay, that's important, right? That's one of our 2 major pieces. Okay, next up, we've got Wes. He also joined me this semester. And he is looking more on the energetic side of things. Okay? How can we manipulate the interaction energy of the urea receptor and the anions that we're looking at by changing small pieces of the receptor? So the thing that he began looking at was, okay, if I have urea and it's decorated with some phenyl rings, some cyclic structures, if I change out this oxygen atom for a sulfur atom, what happens? Okay, so he used computational methods just as my whole group is doing, and he identified that the interaction energy between diphenyl urea and chloride is negative 35.97 kilocalories per mole. This is just a unit that's quite useful. But whenever he interchanged oxygen for sulfur down here to thiourea, the interaction energy became more stabilized. So by just changing the identity of that oxygen for sulfur, we get 4 kilocalories of stabilization. That's awesome, okay? That's exciting. This change, though, changes the acidity, basically the ability of these protons, these hydrogen atoms, to be stolen from the urea compound. And so there's a fine line here of increasing this interaction energy and not having your hydrogen atoms be stolen. So we're still trying to understand where is the fine line here and how can we manipulate that. Another way that he's looking at exploring the energetic environment of these urea receptors with respect to anions is by further decorating them. So taking the phenyl group here, and instead of a hydrogen atom at the different positions, putting things like fluorine and nitro groups and methyl groups. So we can see how these substituents on the phenyl ring change the polarity of this dipole, and they can influence the interaction energy of the urea receptor with the anion. Whenever we have substituents like fluorine on the phenyl rings, we have been able to see that the interaction energy gets stronger. And so that's the direction that we want to go, is improving the interaction energy, but finding the fine line of what is this compound actually going to do in solution, okay? Okay, finally, last but not least, is Miss JD. She has been working with me for the past year, and she's been looking at the influence of both architecture and the energetic environment of the host to bind the guests, the anionic guests. And so what she's looking at is this compound. It's been a little bit of a star player in this presentation. So here we have 2 urea groups. Each urea has a phenyl substituent on it, and the 2 groups are bridged by anthracene. Okay, so what JD asked is, can we describe the interaction energy of the whole complex as it binds to chloride as some sort of algorithm, okay, incorporating a structural component where the urea groups are bridged by this anthracene bridge, and so the bridge plus some type of energetic component that we use to understand using the fragment of the urea with just its phenyl ring attached to it. Okay? So can we understand the overall interaction energy of some algorithm by adding the architectural piece and the energetic piece? And so we came up with this idea that interaction energy is of X times the bridge plus Y times 2 times the fragment. There are 2 fragments. This is our fragment. There are 2 of these on our overall complex. And so can we look at how is this what are the influences of both of these pieces when X and Y add up to 100%? Okay, what is the weighting of architecture versus energy? How do those play out? Okay, so first she began by looking at the difference in the guest. And so she's trying to understand here the architectural influence. If we take this complex and we change out fluoride, chloride, bromide, okay, so increasing the size of the anion as she goes from fluoride to chloride to bromide, how does that influence the overall interaction energy? What is the structural component and what is the energetic component? What was really interesting is, as we see, as the anion gets larger and larger and larger, the interaction energy gets smaller and smaller. Okay? And a considerable component of that is because the contribution due to the architectural fit of the host around the guest gets worse and worse and worse. From about 52%, so equal weighting with the energetic component, to 32% to 7%. Man, we had to recheck this number because it seems ridiculous. The interaction energy of this bridge with bromide, it's like 10 kcals per mole. So let me translate that for you. It's awful. It's just awful. It's terrible. It doesn't fit at all. Okay, bad. Just doesn't work at all. Okay, so this tells us, okay, that anions in the size range of fluoride especially, and even chloride, are pretty good fits for this bridge, for this anthracene bridge. Okay? So the architecture is very important, and it helps us understand this bridge is garbage for bromide, but it's pretty decent for chloride and quite good for fluoride. Okay? Whenever we see here these percentages, the fragment, the interaction of the anion with the fragment is compensating for the poor interaction of the anion with the bridge. We're looking in more depth at understanding this in even more detail, but she also, not only did she look at the architectural component, she also looked at the energetic component. Okay, specifically looking at, if I keep the same anion, so chloride, 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 the bridge component is not changing. So the architecture of the bridge is staying the same, but what is changing here is a substituent on the very end of the phenyl ring. So going from hydrogen to nitro, a nitro group, or from hydrogen to a methyl group. Carbon bound to 3 hydrogen atoms. Okay, so let's go back to this algorithm. I really love algorithms when it comes to chemistry. So here is our algorithm that we're working on. If we have our normal, standard, complex, bound to chloride, the interaction energy of the complex with chloride is 32% due to the architecture. Okay, and 68% is due to the fragments interacting with the chloride. That is the way the numbers worked out. So if we think through, if we take just the fragment of our new complexes with the nitro group and with the methyl group, and we calculate the interaction energy of the fragment and chloride, multiply that by 2, and substitute that in to this algorithm. Okay? The bridge is not staying the same, that's not changed. What we're changing is just the interaction energy of the fragment with chloride. If we do that, we predict that the interaction energies of the complex with the nitro group should be about negative 72 kcals per mole. And the interaction energy of the complex with the methyl groups on it should be about negative 58 kilocalories per mole. Okay, so we've used our algorithm, we've made a prediction, and then she ran the complexes. Okay, so here we have a green dotted line that tells you very little just yet, but let me explain this to you. On the left-hand side, we have the actual interaction energy after JD did her calculations, and we'll get there in a second. Here we've got the algorithm of the predicted interaction energy. If the experimental or the computational data is exactly in alignment with our calculations, all of the data points will line up on the green line. Okay, this is the goal. Ideally, this is our hypothesis. Okay, so let's see. Whenever she did the calculations, we get these 3 dots. So the green line is based off of the typical complex of just hydrogen atoms in those substituent positions. Okay, great. Whenever she calculated the complex with the nitro group, it should be about here. Okay? Instead, the interaction energy is stabilized considerably. Okay, it's not on the green dotted line. Okay, if we look carefully at this up here, this is the methyl substituent. If it were perfect, it would be on the green dotted line, but in fact, the actual interaction energy is just slightly less stabilized than what our calculations predict. Okay, so our calculations don't quite accommodate all of the complexity that's happening here. Okay, and so these differences are really interesting to us. The differences, if you want to think, like, how much are they different? So if we have our methyl substituent, the difference is only about 1/4 of a kilocalorie per mole. Not a giant difference, but a difference. Something we can at least identify. The difference for the nitro substituent is more considerable at about 2.3 kcals per mole. Difference from what was expected. Now this results because of long-range changes to the polarity of the nitrogen-hydrogen bond. So by changing the substituent over here, we are changing the polarity of this interaction. A small change, but quite a considerable change in terms of the interaction energy. Okay? And so we're looking more in depth at why? Okay? And how can we account for the differences whenever we change these substituents? Okay, so this is what gets me really excited when I share this story with people. Our algorithm is pretty decent in the grand scheme of things. Great, but it's not quite there. And we can seek to understand, now why is this not exactly lined up with this green dot? Okay, so that is one of the questions that we are seeking to understand in the future. Okay, so as we are going towards the future, I've got 3 great research team members. Everybody's got their own project. We're adding more ideas, but these are the main ones that we care about. Can we continue to understand better the interactions of these urea-based receptors with anions? Okay, can we do that better and better and better? Can we design receptors that have the right architecture, the right shape and fit for the anions that we care about? And can we also understand how can we modify and improve those interaction energies between the receptor by changing out the substituents on the fragments? Okay, and so we're looking at all of these pieces individually, but also how they relate to each other. Is there some cooperation, or what does that look like? Okay, and so we really care about this idea. This long-range changes result in significant and interesting changes in the interaction energies. And so when I think about this, I get really excited because I know that this is the very beginning to a long research endeavor. Chemistry research takes a long time, but we are making progress in understanding more and more of what these interactions can look like and how can we improve them with the target of developing receptors to help others identify this contamination. Now I want to circle back really quickly to my friend's story. About a year or so after I received that first email from my friends in Africa, I saw on Facebook, sources of lots of knowledge, right? I saw on Facebook a post of one of the daughters. She was an art major at the time, and while walking through this really challenging situation, God had already begun to show his faithfulness and his ability to redeem this situation. In fact, she put together an art exhibit showing just that. She took 100 pill bottles that she and her sisters had to take in order to counteract the effects of ingesting such high concentrations of fluoride. 50 of those pill bottles she left just as they were to identify the stark reality of the brokenness of the situation. But the exciting thing is that she took the other half and beautifully designed them, painted them, and through this exhibit was able to identify and share with others that God was redeeming the situation, that he cared for them and was growing them through that, which was a really hard process. And so for me, one of the pieces to just being barely related to this story, just a friend of this family, I see God working in really weird ways. Through one email, God has inspired this opportunity to take what I was studying and to draw me into asking more questions with a target of helping and loving on my friends. And so that, at the end of the day, is the goal, but it's really cool to see that even before I began working on any of this research, even before I really had a clue of what the final piece was for my friends, God was at work. And so my job is simply to join with him. And so by doing this research, that is what I get to do. I get to join with him as he takes this story and works through it in lots of different ways. So, when I think about the idea of joining with God and what He is already doing, especially through this research idea, it's like, oh, okay, research, yeah, let's do this. Like, it's going to be a lot of work, but okay, let's do it. I get really excited about it, but I do know that it will be challenging. And so I think our attitude, when we respond to what God has for us, when we respond to the opportunity to be good stewards, our attitude matters. God talks about this. He says the idea that generosity is important to Him. He loves a cheerful giver. So as my group continues to do research, I desire that we would all do so with the idea that it is a generous opportunity to praise God. When in 2 Corinthians 8 and 9 has a lot to say about generosity, but this is kind of where it goes to for me. In verse 6 it says, the point is this: whoever sows sparingly will also reap sparingly, and whoever sows bountifully will also reap bountifully. Application. Let's do a whole lot of calculations. Let's sow the seed of lots of calculations so we can get lots of results. Yes? Yes. Also, the ministry of this service is not only in supplying the needs of the saints, but is overflowing in many thanksgivings to God. What a cool opportunity to do chemistry that helps people praise God. Wow, weird. Okay, and then finally, Isaiah 12, 3 and 4 comes to mind. With joy you will draw water from the wells of salvation, and you will say in that day, give thanks to the Lord, call upon His name, make known His deeds among the peoples, proclaim that His name is exalted. My ultimate desire for all of this is that people will draw water from wells of pure water. And as they have access to safe water and are able to identify that their water is in fact safe, that along with that, they would draw waters from the wells of salvation of the good news of Christ. And that would be intimately coupled with this idea. And that at the end of the day, they too would praise God, right? Like, that is such an awesome opportunity. And so for me, that is my motivation. And so what I want to ask you to end on this question is, how will you be generous out of your current experiences? Out of your current educational opportunities and life experiences, how will you obey and be generous? I think that's a big question, and so I leave this with you guys to process on over time. And so with that question though, I have some acknowledgments. So I want to acknowledge my team of researchers. They have done the lion's share of all of this work, and so wonderful job. Thank you. Okay, so we've got JD Edwards, Caleb Langdon, and Leslie Shorey. I also want to acknowledge that this has been made possible by the JBU Division of Natural Sciences and their support, and so I really appreciate all of that, how they have supported me. This work was in part supported by the JBU Summer Scholar Fellowship and the Christian Scholars Foundation grant, so we look forward to this upcoming summer with my research team. And with that, I will take questions. What questions do you all have for me about this? Yes, sir.
So, would finding contaminant be different than removing the impurity?
Yes, that's a really big, important piece about chemical contaminants. When we think about the sheer number of molecules in a mole of molecules, okay, 6.022 times 10 to the 23rd, that's a whole lot of molecules in one mole. Okay, and 1 mole of fluoride would be not very much at all. Okay. And so, since that would be so many molecules to have to identify, selectively pull out of water, and then deal with the waste of that, the solution is, in order to be efficient, is to find the source. Identify that there's a problem, and then fix the source so that the contamination stops happening. So, purification is really important when it comes to microbial contaminants, but purification with respect to chemical contamination is going to be a challenge. You're going to exhaust all of the urea receptors known to man well before you have run out of water to purify. Yes?
Once you've found this molecule you're looking for, would the next consider, like, how will that be able to be affordable for this country? Like, would the procedure be really expensive to pass use?
The reason I'm using urea as a building block is because urea is relatively cheap. So my desire would be to target receptors that would be able to be integrated into some type of material, whether it's a polymeric material or something along those lines, to where we could generate those polymers relatively cost effectively. What I would really love to is if we could generate a polymer that would identify the contaminant, and then if you just heated it up and you just shifted equilibrium, and then you could reuse it. But we shall see. That's the goal, though, is to identify receptors that are not cost prohibitive. But we've got a little ways to get to before we get to that. Yeah, great question, thank you. What else? Any other questions? Yes, ma'am.
What makes you change just the substituents on the fragments and not changing the bridge?
Those are two different questions, and so what we have begun to do is we want to change one thing at a time. Changing the substituents on the bridge would have an impact on the interaction energy, but we haven't gotten there yet. So, that's a good question, though. Absolutely. It'll influence things. We haven't had the opportunity to test all those things just yet. What else? Other questions? Sorry, yes, sir.
So, you're doing the research particularly with fluoride contamination. Is that one of the more common chemical contaminants?
From what I can tell, it's one of the, especially one of the more health problematic. That's not the right way to say that, but it causes pretty severe side effects, and so I think it is relatively common, relatively speaking, but it also has pretty significant impact on people's lives, and so that's part of the kind of the combination there. Yeah. Yes, ma'am.
This is kind of like less of a science question, more of a personal question, but
Okay.
if there was one, what was the point throughout this that you just felt kind of like you were stuck, or if there were a block, and just kind of like, what was that like? Because this just seems so like big and new. It's like, kind of like, how did that work?
So I got the email from my friend 4 years ago. The idea for the research project was 2.5 to 3 years ago. And so there was about a year and a half of stuckness, which is a considerable time frame. And so I think part of it was, as I began to learn more about supramolecular chemistry and about the problem, I was able to see those pieces converging, and it just took time for me to identify how do these really relate. At first, the question was about galvanized water tanks, and I didn't learn about galvanized tanks of any kind. But beginning to see how could that relate to the pieces that I didn't understand, that progression just took time. My process for that was a lot of thinking, and then leaving it for a few weeks, and then it would come back around. And so I'm very much an internal processor, and so for me, being free to internally process for a year and a half was helpful. Any other questions?
A question and then perhaps a humorous thing, but we'll get to that.
Okay.
Well, so I know, for example, a lot of city water treatments that they have some amount of fluoride in them.
Yes.
And so is there a particular threshold you're looking for, or just any presence of fluoride?
So the idea would be eventually to get to where the receptors changed color. They gave some kind of indication at a specific threshold. You're exactly right. A small concentration of fluoride is actually really important for us. But too much is really also very unhelpful. And so trying to have perhaps a distribution of molecules that would help understand concentrations would be helpful. We're not quite there yet.
That's okay, dark means dangerous, red is dead.
Yes, yes, yeah.
I was wondering if we could go back to
Okay.
the one, the different models you're looking at. There was one that looked a lot like a mouse snowman. I just think that flashing up there.
These? Or keep
Over the
going?
back.
Okay. Mouse snowman.
There.
Which one are these?
Yeah.
Oh.
This one's like version of superheroes right now.
undergrads who are looking to do things like this in the future, how we can prepare ourselves now for making an impact in the future?
That's a great question, and that's a giant question. I would say there are two things. First, pursue Jesus with all you have. Know Jesus. Know him better. Be more like him. Find people that will help you become more like Jesus. Be discipled. Second, be good at your work. If we go into the world and we are terrible scientists, why should anybody care about the things we feel and believe? We are not, our value is in no way determined by our ability to do science or our capacity to have some amazing, eloquent defense for our faith. Our value is not determined by that. But in the scientific world, our voice is heard best when we are able to present ourselves as good scientists. I think it opens the door for conversations with people about your faith and your motivation. And so I would say those two things. Pursue Jesus, know him, be more and more like him, and be good at your science. Yeah, good question. Thanks.
Thank you all. I think with that, we're going to have to wrap it up. Please give a word of applause to